Mic check, 1, 2. All right, looks good. So I can confidently say these are good choices here. We're gonna keep working through the LPIC-1. So let's keep going without any delay. All right, so resizing EC2 slash 3/4 partitions. Parted can be used to resize partitions to make them bigger or smaller. However, there are some caveats. During resizing, the partition must be unused and unmounted. You need enough free space after the partition to grow it to the size you want. I don't know what that means. Um, so does that mean that you can't have a partition that totally encompasses all space on the disk, and you have to have like some amount of like buffer space after your last partition? The command is resize part followed by the partition number and where it should end. For example, if you have the following table, so we're going to end it at 300 meg, trying to grow partition 1, which ends at 98, using resize part would trigger an error message because with the new size partition, partition 1 would overlap with partition 2, and it looks like it actually already does. Oh no, sorry, that was the size, so we got to pay attention to our column headers here. So right now it ends at 99.6, so if you resize it to 100, it would overlap, which you can't do, so you get an error. However, partition 3 can be resized as there is space after it. Okay, so that's just what they mean. I'm overcomplicating things. So partition 3 can be resized to just whatever the full length of the full size of the disk is fine to resize it all the way out there. They're just saying like you can't overlap with other partitions. So like this, if this was a partition from 300 to 400, you could resize this to 300. So, however, partition 3 can be resized as there is space after it, which can be verified with the command print space free in parted. So we've got parted open here. We're going to do print free, and we can see we've got our SCSI disk there. And there we go. Okay, so you can use the following command to resize partition 3 to 350 megabytes. So here it is, resize part. Part stands for partition. We're going to resize the third partition here, which is right here. We're going to resize it to 350. So let's check that this is not going to bump into another one. Okay, so it looks like, yep, there's not a fourth partition there. There's nothing beyond this. We do have this extra row here, but we can see that it's just our free space. We can see that marked here. So our first partition actually doesn't. There's actually some free space before the first partition as well, but the free space starts at 300. So we're totally fine to expand this partition here without any conflicts. So we're going to expand it to 350, and there we go. Remember now that the new endpoint is specified counting from the start of the disk. So because partition 3 ended at 300 megabytes, it now needs to end at 350 megabytes. So it's from the start of the disk, not from the first partition. So as we saw, we've got some free space at the beginning. So that's important to remember. But resizing the partition is only one part of the task. You will also need, oh, that's horrible. You will also need to resize the file system that resides in it. Man, I could see that creating all kinds of situations. For EX2/3/4 file systems, this is done with the resize to FS command, and it looks like that's done with this number 2 here, regardless of which file system it is. In the case of the example above, partition 3 still shows the old size when mounted. So because we did not update the file system, when we mount the disk and we look at the file system is still sized to the size it was under the original partition. The update is not reflected in the file system until you explicitly resize the file system after you resize the partition. To adjust the size of the command resize to FS, device size can be used, where device corresponds to the partition you want to resize, and size is the new size. If you omit the size parameter, it will use all of the available space of the partition. Before resizing, it is advised to unmount the partition. And is that before you resize the partition or before you resize the... So to adjust the size, the command... So this is to resize the file system, can be used, where device corresponds to the partition. File systems are stored within partitions, so you need to feed it the partition. Yeah. Wait, what? Oh, I think we have another typo, actually. I really do think we have another typo. So we're learning about a new command here. So we just learned about this command, resize part, and that's pretty intuitive for what it does. It resizes the partition. But now we're learning about a new command here called resize to FS. And this is not quite as intuitive because this 2 here, I guess I don't really understand. If it was just resize FS, that would be a more intuitive command for me. But we can see this command, this writing here. It says to adjust the size, and the size of what too. This is where it gets confusing. But resizing the partition is only one part of the task. You also need to resize the file system in it. In the case of the example above, partition 3 still shows the old size when mounted, and by size they mean the old size of the and this is really confusing. So what they're saying here is that partition 3, so when we do a df-h on partition 3, it shows the file system. So we can see it lists the file system, and then it shows that the size of the file system is the same size it was before we increased the size of the partition. So it's very unclear here, because it says in the case of the example above, partition 3 still shows the old size when mounted. So this is kind of a full statement. It's kind of correct. It's just a murky, unclear statement. So how I would rewrite this is, in the case of the example above, the file system shown as a result of running this command on partition 3 on the disk B still shows the size of the old partition, of partition 3 before it was increased. So to adjust the size, and then here's where it gets really tricky, because the size of what? The partition, the file system. I think it's safe to assume that we're talking about the size of the file system. So to adjust the size of the file system, the command resize to FS, with this unclear 2 there, device size can be used, where device corresponds to the partition you want to resize. But that's wrong. Device doesn't correspond to the partition you want to resize. Device corresponds to the partition that holds the file system you want to resize. So tricky to keep these concepts right. And then the size parameter is the new size of the file system. If you omit the size parameter, it will use all of the available space of the partition. So by default, it just uses the full size of the partition. So remember that partitions of file systems are separate, and you must use separate commands to modify them. And you have to modify the partition first if you want to increase the file system, unless you haven't created a file system that uses the full space of the partition. But I'm not sure why you would want to do that. Maybe there is a reason. So before resizing, it is advisable to unmount the partition. See, I wish they would be so much clearer here and say before resizing the file system, it is advised to unmount the partition. It would just be so much easier to understand if they were that clear. But anyway, moving on. In the example above, sudo resize 2fs, and then now we feed it the partition where the file system presides. So we're going to resize the file system on this partition to 1K blocks. Okay. And then the next thing we're going to do is check the size now. So here's the partition that's residing here. Now, one thing we can't see, which is kind of a problem, is, you know, if it says it's a file system, it looks like all we can see is where the file system resides, but we can't see any information about what the file system is, if it's a FAT, if it's a EXT, if it's a better FS. Kind of need to see that. So it's kind of too bad that the information about the file system itself seems to be lacking from a lot of these commands. To shrink a partition, the process needs to be done in the reverse order. First, you resize the file system to the new, smaller size. Then you resize the partition itself using parted. Warning, pay attention when shrinking partitions. If you get the order of things wrong, you will lose data. Okay, so in our example, resize 2fs. There we go. So this is where the file system resides on this partition. We're resizing it. Yeah. So and see how it does it by the blocks that were set up. So, and then yeah. So it's the size beyond where it started. Okay, and now we'll do the parted command to look at our results. So now we're gonna shrink it, shrink the partition. So we're resizing the file system, then we're shrinking the partition, and then we're printing out the partition. So tip, instead of specifying a new size, you can use the -M parameter of resize 2fs to adjust the size of the file system so it is just big enough for the files on it. Okay, so you can automatically make the file system as close to the size of the partition as is possible. So I can't really imagine a scenario where you wouldn't want the file system to be as large as the partition. So I guess that scenario is very uncommon, so much so uncommon that there's a special option -M to not have to think about that scenario. So let me ask the AI just one thing. Tell me if there would ever be a situation where you would want a file system to on a reside within a partition where the size of the file system is significantly smaller than the size of the partition. Okay, so here we go.
Yes, there can be situations where you would want a file system to reside within a partition where the size of the file system is significantly smaller than the size of the partition. This is a common practice and
Oh,
can serve
really?
various
Okay, that's
purposes.
surprising.
One, reserved space. In some cases, administrators intentionally create file systems with some unused space to serve as reserved space. This reserved space can be useful for handling emergencies, preventing the file system from becoming full, and ensuring system stability. For example, this space can be used for log files, temporary files, or to accommodate unexpected increases in data. To future expansion, you might allocate a smaller file system initially because you have plans to gradually expand it over time. This approach allows you to efficiently use available storage resources while avoiding overallocation until necessary. 3. Backup or snapshot space. You might reserve a portion of the partition for creating backups or snapshots of the file system. This ensures that there's enough space to create backups without impacting the primary file system's operation. 4. File system type flexibility. Sometimes, you may want to keep the option open to change the file system type or use a different storage technology in the future. By not fully utilizing the partition space, you leave room for migration or transformation without needing to resize the partition itself. 5. Performance optimization. In some scenarios, allocating a smaller file system within a larger partition can lead to performance improvements. Smaller file systems can potentially reduce file system management overhead and fragmentation. 6. Compatibility. Certain applications or legacy systems may require specific partition sizes or alignments. By creating a smaller file system within a larger partition, you can meet these requirements while still efficiently using the available space.
Oh, that makes sense.
In summary, there are valid reasons to create a file system that is smaller than the underlying partition. It offers flexibility, stability, and adaptability in managing storage resources, depending on...
Okay, so I guess the one that makes the most sense to me is if you're trying to set up a legacy system for whatever reason, just for research or whatever, and the legacy system has a file system table, or a file system that is has to be a specific size, and that size is much smaller than your partition. Probably is likely the case if it's a legacy system. So there's no need to blow away a partition. Like if you're just gonna do it temporarily and then put your other one back, just leave your partition alone, put on that smaller file system, do what you need to do, and then blow it out and then repurpose it. So it's all about in the end, it's really all about your disk, what you're going to use it for. If you have another disk you're going to use for other things, if you need to repurpose this disk and use it in different scenarios for different contexts. So in the end, that's really what matters. And I guarantee you the problems I'm having in my home lab, my Dell 610 Dell PowerEdge, with adding a new device. Now that I think of it, I guarantee you the problems is probably with partitioning and the file system on it. So I bet I could get it to work. It's just it's just a little bit tricky. I do have I could work on this. I believe. Yeah, I definitely could work on this. Okay, but anyways, we'll work on that later. So where were we at now? Oh yeah, we were looking at this whole section. So yep, and I finished reading here. So the next section is creating swap partitions. On Linux, the system can swap memory pages from RAM to disk as needed, storing them on a separate space, usually implemented as a separate partition on a disk, called the swap partition or simply swap. This partition needs to be of a specific type and set up with a proper utility, mkswap, before it can be used. To create the swap partition using fdisk or gdisk, just proceed as if you were creating a regular partition as explained before. The only difference is that you will need to change the partition type to Linux swap. On fdisk, use the T command, select the partition you want to use, and change its type to 82. Write changes to disk and quit with W. On gdisk, the command to change the partition is also T, but the code is 8200. Write changes to disk and quit with W. If you are using parted, the partition should be identified as a swap partition during creation. Just use Linux-swap as the file system type. For example, the command to create a 500 megabyte swap partition starting at 300 megabyte on the disk is parted make part primary, so that's the type, which shouldn't matter if it's now here's the thing that's tricky. We don't know what the file system is, but it doesn't matter what the file system is because this is the partition. So you create the file system after you create the partition. So we can make a primary partition. We can make an extended partition. It depends on your I think your like whether you're using the BIOS or the UEFI. I think matters for that. But then we're gonna create Linux swap, and notice how we're starting at 301, which is kind of interesting, and then to 800. Once the partition is created and properly identified, just use mkswap followed by the device representing the partition you want to use, like so. So mkswap /dev/sda2. To enable swap on this partition, use swap on followed by the device name. So swap on /dev/sda2. Similarly, swap off followed by the device name will disable swap on that device. Linux also supports the use of swap files instead of partitions. Just create an empty file of the size you want using dd and then make swap and swap on with this file as the target. The following commands will create a 1 gigabyte file called myswap in the current directory filled with zeros and than, so the comparison form of than, not the time bound if then version of then, set up and enable it as a swap file. So we got a typo there, which is kind of distracting, especially since I shouldn't talk about this, but okay, well, just between you and me, you being the entire public internet all throughout eternity, independent of location and time, I actually took a job interview where they had a proprietary version of the SAT. Job interviews can be insane sometimes. And I don't know, I just did really, really bad on it because, like, I've just, life can be rough sometimes. Sometimes you're not on your A game. And then I sent this like follow up email, kind of like the thank you email you're supposed to do, and I just like I used the wrong form of then in my email. I used THEN instead of THAN, and I didn't like get called out on it or anything, but it's just like I'm smart enough to know how dumb I am, and it pains me every day. Okay, but anyway, that's a personal private story that I decided to talk about because I am smart enough to know how dumb I am, and thought that was uh, and behaved in a dumb way. All right, so next section is create the swap file. So dd if equals slash dev slash 0 of equals my swap, bs equals 1 megabyte, count equals 1024. So okay, so we're going to set it up and enable it as a swap file. There we go. So if equals is the input file, the source of the data that will be written to the file. In this case, it is the slash dev slash 0 device, which provides as many null characters as requested. Of equals is the output file, the file that will be created. BS equals is the size of the data blocks, here specified in megabytes, and count equals is the amount of blocks to be written to the output. 1024 blocks of 1 megabyte each equals 1 gigabyte. Make swap space my swap. So there we go. And then swap on equals my swap. So I don't remember these commands. I don't remember where they were. Oh, here we go. So they were brought up here. So let's go back and review the make swap command. Here we go. So once the partition is created, then we use make swap to convert the primary partition that we made to a swap partition. And then we have to turn the swap position on using swap on, and we can turn it off. So I mean, if you think of what a swap partition is, you know, it makes a lot of sense that you would want to turn it off or on, because you know, it like churns up your disk and stuff. It like, you know, it's something that you might want not always to be on in every case. Okay, so okay, and I don't remember. Oh, right. So we were right here. So, okay, we're almost done here. So using the commands above, this swap file will be used only during the current system session. If the machine is rebooted, the file will still be available, but will not be automatically loaded. You can automate the loading of the file, by adding the new swap file to /etc/fstab file system table, which we will discuss in a later session. Tip: both make swap and swap on will complain if your swap file has insecure permissions. The recommended file permission flag is 0600. Owner and group should be root. So you don't want anyone to be able to just access your swap file willy-nilly. That's an important file to have locked down. So I've got a number of questions for the AI. Let's ask each question one by one. Let's see what it has to say about just this section, because I thought this section was a little bit tricky to follow, and then it did have that big kind of like grammatical error in it. So let's hear what it says.
The provided content offers a detailed explanation of how to create swap partitions and swap files on a Linux system. Swap memory plays a crucial role in managing a system's memory by allowing the operating system to offload less frequently used data from RAM to disk when necessary.
Okay.
Here's an analysis and opinion on the content. 1. Explanation clarity. The content is well structured and provides clear step-by-step instructions for creating swap partitions and swap files using various tools such as fdisk, disk, and parted. It also explains how to set up and enable swap using commands like mkswap and swapon. This clarity is helpful for users, especially those who might be new to Linux. Two variety of methods, the content covers both swap partitions and swap files, offering flexibility to users based on their system requirements. This is a good approach because different situations may call for different solutions. 3. Usage of commands. The content explains the purpose and usage of various Linux commands like dd, mkswap, swapon, and swapoff. This is beneficial for users who want to understand the underlying processes. For security consideration, it emphasizes the importance of secure permissions, 0600, for swap files and mentions that the owner and group should be root. This is an important security measure that should not be overlooked. 5. Lack of context. The content provides detailed technical instructions, which are valuable for those with prior knowledge of Linux. However, it lacks context for beginners who might not understand why they need swap or when it's appropriate to use
Yeah,
swap
that's why you
partitions
take
versus
your
swap files.
essentials.
Some
Linux
introductory
essentials.
information could be beneficial. 6. Updates and versions. Linux systems evolve over time, and different distributions may have variations in commands or methods. Users should always check the documentation specific to their Linux distribution to ensure compatibility with the instructions provided. In my opinion, this content is informative and comprehensive for users with some familiarity with Linux.
Yep, that's me.
It effectively guides users through the process of creating and managing swap memory, which is a critical aspect of system performance and stability. However, it could benefit from a brief introduction explaining the purpose and importance of swap in a Linux system, especially for those new to the topic.
All right, so if that doesn't describe you and you agree with the AI, get your essentials first. You're just not there yet. For me, I know what swap does. It makes it so that you're not dead in the water when you run out of RAM. It just uses the swap space, and it can also be used for like optimizing for like caching things that you constantly have to move back and forth between RAM and your disk for, or just like put it in swap. But my question is, when it comes to swap, how did the introduction of solid state drives change this concept? Was it able to remain relevant in? How was it able to remain relevant in light of such a drastic technological advancement? Why not develop new concepts rather than relying on old ones like swap? Like solid state drives are a lot.
The
Like,
introduction of solid-state drives,
yeah.
SSDs, did indeed impact the concept of swap in Linux and other operating systems. Here's how SSDs changed the landscape and why swap remains relevant. 1. Performance improvement. SSDs are significantly faster than traditional hard disk drives, HDDs, when it comes to read and write operations. This improvement in storage speed has reduced the need for swap to some extent. When swap space is accessed on an SSD, it is much faster compared to accessing it on an HDD, reducing the performance penalty associated with swapping. 2. Extended lifespan. SSDs have a limited number of write cycles compared to HDDs. Frequent swapping can lead to more write operations on the storage device, potentially decreasing its lifespan. To mitigate this, modern SSDs are designed with wear leveling algorithms that distribute write operations evenly across the storage cells,
Oh, that's cool.
thus extending the lifespan. 3. Larger RAM. Advances in hardware technology have made it more affordable to include larger amounts of RAM in computers.
I do have one more question.
As a result, many modern systems have sufficient RAM to handle most workloads without the need for frequent swapping. This has reduced the reliance on swap space for performance optimization. 4. Swap on SSDs. Some Linux distributions and users choose to place swap partitions or swap files on SSDs to take advantage of the SSD's speed, even if they have ample RAM. This allows for faster swapping when it does occur. 5. Hibernation. Swap is still essential for hibernation, suspend to disk, Functionality. When a computer hibernates, the contents of RAM are saved to the swap space, allowing the system to resume its state when powered back on. Without swap, hibernation would not be possible. 6. Resource safety net. Swap continues to serve as a safety net for unexpected situations where RAM may become depleted due to resource-intensive tasks or memory leaks. Having swap space available can prevent system crashes by providing a space to temporarily store data that can't fit in RAM. Regarding the question of developing new concepts rather than relying on old ones like swap, it's important to note that while SSDs have changed the landscape, the concept of swapping data between RAM and storage is a fundamental aspect of memory management in computing. Developing entirely new concepts to replace swap would be challenging because the need for secondary storage as a memory extension or overflow space remains relevant in various computing scenarios. Instead of replacing swap, modern computing focuses on optimizing and adapting swap mechanisms to the characteristics of the underlying storage technology, such as SSDs. This allows for better performance and longevity while preserving the fundamental concept of swap. Additionally, advances in virtual memory management, file system technologies, and memory-efficient programming have also contributed to the continued relevance of swap in contemporary computing environments.
Okay, so that was interesting. So instead of replacing swap, modern computing focuses on optimizing and adapting swap mechanisms. So swap is just, this thing that allows you, like as a concept, swap is good because it's just like saving the space that you can do cool things with. So yeah, so regarding the question of developing new concepts rather than relying on old ones like swap, it's important to note that while SSDs have changed the landscape, the concept of swapping data between RAM and storage is a fundamental aspect of memory management in computing. Developing entirely new concepts to replace swap would be challenging because the need for secondary storage as memory extension or overflow space remains relevant in various community scenarios. So my question is, so regarding the difference between RAM and non-volatile storage such as SSDs, why hasn't technology progressed enough yet so that either RAM is no longer so volatile that other forms of memory matter, or that non-volatile storage devices such as SSDs are fast enough so that RAM no longer matters? Why is there still a need for hybrid memory systems, RAM and SSD, such as RAM and SSD, rather than a single single solution, as there is with CPUs, rather than a single device as there is with CPUs. Okay, so let's see what the answer is.
The differences between RAM, random access memory, and non-volatile storage like SSDs are primarily due to the inherent characteristics of the two technologies. These differences, including volatility, speed, and durability, serve specific purposes in computing, and achieving a single device that combines all these aspects has proven to be challenging for several
But they
reasons.
did it with
1. Speed
CPU,
versus
right?
volatility. RAM. RAM is incredibly fast but volatile, meaning it loses its data when power is removed. This volatility is precisely what allows RAM to operate at the speeds it does. RAM's
I
primary
guess not,
purpose
because
is
they
to
have
provide a
GPUs.
high-speed workspace for the CPU to quickly read from and write to during active tasks. SSDs. SSDs are non-volatile, so they retain data even when the power is off. However, SSDs are slower compared to RAM. Their primary purpose is to provide long-term storage for applications, data, and the operating system. 2. Cost-effectiveness. RAM is more expensive than SSD storage on a per gigabyte basis. It's not feasible, both economically and technologically, to have the entire storage capacity of an SSD operate at the same speed as RAM. 3. Wear and tear. RAM has limited write endurance compared to SSDs. Writing to RAM repeatedly, like you would with storage, would wear it out quickly. SSDs are designed to handle a larger number of write cycles, making them suitable for long-term data storage. 4. Energy consumption. RAM consumes power even when it's not actively in use, which is why it loses data when power is cut off. SSDs, on the other hand, are more energy efficient
Oh,
and
that's
can
a good
retain data
reason.
without constant power supply.
That's a really good reason.
5. Parallelism and specialization. CPUs are a single device because they are designed to handle a wide range of tasks. Memory and storage serve different purposes. RAM is optimized for low latency, high-speed data access,
Yeah,
while SSDs are optimized for capacity and long-term data storage. Combining these functions in a single device would involve trade-offs that
right.
might not be suitable for all computing needs.
That's a good one.
6. Hybrid memory systems. Hybrid memory systems, which combine RAM and SSDs, aim to strike a balance between speed and capacity. They use RAM for frequently accessed data and SSDs for less frequently accessed data or for storage. This approach optimizes performance and cost effectiveness. In summary, technology has not yet progressed to the point where we can replace both RAM and non-volatile storage with a single device without significant trade-offs. The differences in speed, volatility, cost, and durability between RAM and SSDs make them suitable for distinct roles in computing. Hybrid memory systems, along with caching and optimization techniques, help address the performance gap and provide a balance between speed and storage capacity in modern computing architectures.
Okay, so this answer here is the one that really jumps out the page. So like even if we did have a single device that we could use for the purposes of if we had like a single piece of technology that did the same things as RAM and the same things as non-volatile memory, we would want to optimize that technology in different ways, or we would still want to use it as two separate devices because we need a device that takes very little energy and basically just sits there doing nothing until you need it to do something, and that is just hold the things you're not actively using right now, all your files and everything like that. We need a device to just sit there and not draw power and not be power hungry and waste energy and just respond when it needs to respond. And then we need the opposite of that. We need a device that's always on, always working, and allows you to move your mouse without your mouse lagging. So like, even if we just had one uh, unified device that could do everything SSDs could do and could do everything RAM could do, we'd still probably need to use two of that same kind of device, and we need to have one of those be hyper optimized to do what RAM does, and then the other one be hyper optimized to do what SSDs does. So it doesn't really have anything to do with uh, manufacturing, production, and actually designing the technology, the capability to do that. It just has to do with like what you need a computer for. And like if you think of like what you need a human body for, like if you made the eyeballs out of the same material as you made the lungs, like you'd still want them to do different things because the lungs and the eyes have different functions. So you'd want the lungs to be able to inflate in and out like a sponge, but you definitely would not want your eyes to do that. You'd want your eyes to be able to hold their shape, and not expand or contract in the same way as your lungs. So it's like the answer to like this idea that technology hasn't progressed enough, so that RAM is no longer volatile and that storage devices are no longer slow. Well, that's not the case. RAM really isn't that volatile probably anymore. Storage devices definitely aren't that slow anymore, especially SSDs. But still, you need two different hyper optimized devices because you've got two different use cases that you need to happen in a hyper optimized way. The first use case is to have the computer run energy efficient. So you need a device that only really responds and draws power when it's required to do so, and as such allows you to do the things that you don't immediately need to do, such as drawing up a file you rarely use, saving to that file, anything you're not actively doing here and now but still needs a place to go on the computer. You want that to go in an energy efficient place that it's difficult for things to go wrong in. On the other hand, you want the things you're doing here and now. It's almost like the difference between UDP and TCP. This is a networking channel, so like it's a different kind of like protocol. Like it's okay for like a little bit of a blip or like the screen to flicker a little bit if that means you can hold a contiguous thought and set of objectives and goals, and you don't have to like come back to it tomorrow to wait for it to finish loading. So like you like it's not really a matter of the technology, like the hardware behind it, not being sophisticated enough or still being underdeveloped. It's a matter of what the computer is actually doing and why. And even if you have the most sophisticated technology in the world, these problems are still going to arise. The problem of doing something here and now with zero latency, and the problem of the machine not hogging up, more power than we can provide it, and not being able to hold on to and store things longer than we need it right here and right now. All right, so my next question is I answered it for myself, but I'm just curious what the AI has to say. So the next question is, but they did it with CPU, right? And they answered, you don't have volatile and non-volatile CPUs, right? Or does the existence of GPUs mean that the same sorts of issues apply to CPUs as well as it does to memory? So I'm going to ask it that, but I think I get it. The first answer is that CPU and memory are just different things. So it's like you're conflating the two concepts, just like how you conflate the function of an eyeball and the function of a lung. So they're just two separate organs with the separate purposes, and you can't really draw parallels from one to the other. And then the second answer is, well, that we have GPUs and we have CPUs, so the same rules apply, where if you need one thing done in a hyper optimized way, you probably need one piece of equipment created for it in a hyper optimized way, and a universal computing device can be universal. That's fine. It could probably do all aspects of the computer to some extent, but you need to hyper optimize it for its specific roles. Like a human cell in an eyeball and a human cell in a lung is still a human cell, but they're hyper optimized for different purposes. But as we're learning about in science, like you can take stem cells and you can you can make like the cells don't come from, different things. Like a cell, like you're born with the sperm and the egg, and then it divides into different cells. So it's like, it's not like you have to have some other mechanism to get the cells in your body depending on what the cells do, but the cells that are a part of your body end up quite a bit different, even though they're born of the same material, because they're hyper optimized for the tasks that they serve. So same thing with a computer.
CPUs and memory, RAM, are indeed distinct components in a computer system, but they serve different functions and have different characteristics, which is why they are separate. Here's how CPUs are different from memory, and why the same issues don't apply. 1. Function. CPU, Central Processing Unit. The CPU is the brain of the computer responsible for executing instructions and performing calculations. It processes data and controls the overall operation of the computer. Memory, RAM, on the other hand, is used to temporarily store data and program instructions that the CPU needs while it is actively processing tasks. RAM provides fast, volatile storage for the CPU to work with. 2 characteristics. CPUs are designed to be fast and perform a wide variety of operations quickly. They are volatile, meaning they lose their data when power is turned off, but this is not a concern because the CPU doesn't need to retain data beyond the duration of a task. Memory, RAM, as mentioned earlier, is also volatile and provides very fast access to data, but it is designed for temporary storage. Its primary role is to support the CPU during active tasks and allow for efficient data access. 3. Specialization. CPUs are specialized for executing instructions and performing complex calculations. They are optimized for high-speed processing. Memory, whether it's RAM or non-volatile storage like SSDs, is specialized for data storage and retrieval. RAM is optimized for speed, while SSDs are optimized for capacity and long-term storage. 4. Parallelism and purpose. CPUs are designed for parallelism and can execute multiple instructions simultaneously using techniques like pipelining and multi-core architectures. Memory and storage serve a different purpose, and the trade-offs between speed, capacity, and volatility are inherent to their roles. The existence of GPUs, graphics processing units, doesn't change the fundamental distinction between CPUs and memory. GPUs are specialized processors designed specifically for graphics-related tasks and parallel processing. While they have their own memory, VRAM, they still rely on system memory, RAM, for various tasks. In summary, CPUs and memory serve different functions in a computer system, and their characteristics are optimized for those functions. The distinction between volatile and non-volatile storage is more relevant to memory and storage components, as the requirements for data storage and retrieval are different from those of a CPU, which is primarily focused on computation. The specialization and separation of these components allow for efficient and balanced system performance.
All right, so curiosity's been satisfied. So let's go on to the guided exercises. Try to finish everything up in this one video. That'd be great. We are near the hour mark, but let's keep going. I'm feeling good. So guided exercises. So the first guided exercise: which partitioning scheme should be used to partition a 3 terabyte hard disk into 3 1 gigabyte partitions, and why? So first of all, let's think about what kind of partitioning schemes there are. So I'm not aware of this is kind of a tricky question for me, because like I don't know, like I didn't know that there were partitioning schemes. And then if there were, what I would think is like a boot partition, a storage partition, and a swap partition. So like that would be a partitioning scheme as far as I know. And you wouldn't do that to partition it into three 1 gigabyte partitions. I mean, you'd have the storage scheme be the majority of the storage partition in the partitioning scheme be the majority of the hard disk. So you'd have it be like over 2.5 terabytes, and then the boot probably would be the smallest one. It's just for the UEFI. If it's for the BIOS, it's probably even smaller. I don't know. And the swap, that would be probably pretty big. That'd be like, 4 gigabytes, something like that. Like enough for like, computers usually have like 4, 8, 16 gigabytes of RAM, so you'd want probably at least 4. I do remember we read something about how big to make the swap partition, but I don't remember that, unfortunately. It probably will be on the test, but I'm just gonna say what I think, and I'm gonna say you want the data, a boot, and a swap partition, and you want the boot partition so you can boot it up. You want the swap partition in case you want out of RAM, and you want the data partition so that you can store your files. That's my answer. All right, so the real answer is GPT. As MBR supports at most 2 terabyte hard disks. So my answer wasn't even in the same planet as the real answer. So let's go back and read up about partitioning schemes. So so here's the partitioning schemes, and it looks like there's only 2 of them. So, and they are MBR and GPT. So there are 2 main ways of storing partition information on hard disks. And you kind of can forgive me a little bit because this is a big section, so we read about this a while ago. That is why we are reviewing it now. The first one is MBR, Master Boot Record, and the second one is GPT, which is Globally Unique Identifier Partition Table. Alright, so MBR, this is a remnant of the early days of MS-DOS, more specifically PC-DOS 2.0 from 1893. It's never going to be MBR. I think it's time to forget about it unless you're doing some kind of historical research for whatever reason. And for decades was the standard partitioning scheme on PCs. The partition table is stored in the first sector of a disk called the boot sector, along with a bootloader, which on Linux systems is usually the grub bootloader, but MBR has a series of limitations that hinder its use on modern systems, like the inability to address disks of more than 2 terabytes in size, and the limit of only 4 primary partitions per disk. So the question was, which partitioning scheme should we use partition a 3 terabyte hard drive? So in fact, the only acceptable answer is GPT because MBR doesn't even support disks larger than 2 terabytes. And it says that right here, GPT, as MBR supports at most 2 terabyte hard disks. So let's read some more about GPT. So GPT, also known as the GUID partitioning system, is a partitioning system that addresses many of the limitations of MBR. There is no practical limit on disk size, and the maximum number of partitions are limited only by the operating system itself. It is more commonly found on more modern machines that use UEFI instead of the old PC BIOS. So modern, here and now, that's what matters. GUID or GPT, which stands for GUID, partition table. So GUID is really all you got to know. Globally unique identifiers. That's the here and now. That's what matters. Now, the thing is, during system administration tasks, it is highly possible that you will find both schemes in use. So it is important to know how to use tools associated with each one to create, delete, or modify partitions. So you will see these, I mean, depending on what you're working with. But don't forget about this one as I just did. All right, so the next one is on Gdisk. How can we find out how much space is available on the disk. And I do not remember this one either. So we know that gdisk is the GUID partitioning tool. So I guess before we look at the answer, let's see if we can just figure it out from the reading of this tool. So let's go back and look at the what was written about this tool. All right, so we've got a section here called managing GUID partitions using the GPT, the GUID partitioning tool or GUID partition table. So we're going to manage those partitions with gdisk. So it's kind of like parted a little bit. So you enter it in, you go into this menu. So so it looks like the answer I would go with is probably like P based on what's written here. So I'm gonna go with P. That's my final answer. Let's see what the real answer is. So the question is, on gdisk, how can we find out how much space is available on the disk? My answer is P. All right, and the real answer, use P, print. The total free space will be shown as the last line of information before the partition table itself. All right, good for me. I got that right. I did have to go back and reference it, but that's okay. So what would be the command to create an ext3 file system checking for bad blocks before with the label my disk and a random UUID on the device /dev/SDC1. Okay, so we're going to create a file system. So that means we need to use the file system tool. So it's something, I think it's MKFS 2 FS if I remember correctly. And then yeah, this is the kind of stuff that's going to be on the good news is this will probably be on in multiple choice. So that will make it a bit less tricky. But if we search for bad blocks, we might, yeah, so we've got some matches on bad blocks. So we definitely need a dash T. So okay, so the other, let's see what else the question was. So we want to create an ext3 file system. So my answer is going to be mkfs.ext3. I think, yeah, .ext3. And that's going to be dash C for sure. Now we got to give it a label and a random UUID. So it's going to be mkfs.ex3 space and then that disk that they said, I think it was actually this one. And then we need to give it a label. So we need dash N to give it that label. And then we need a random UUID. Oh, you know what? It's actually going to be here, but it's the same utility pretty much. So, yep. So dash C still. Oh, actually, it's different. It's going to be yeah, it's totally different. Dash N means trial mode in this case. So it's going to be dash uppercase L. And then dash U, and then we'll type random. So that's my final answer. Let's see if I'm correct. All right, so the correct answer is the command would be mkfs.exe, got it, dash lowercase c, got it, dash uppercase L, got it, my disk, and then dash U and random, got it. And then this I kind of didn't get right because I said to put it here, but if I were to see this as like a multiple choice answer, I'd select this one because I know where it goes. So alternatively, you could use the full command, not just the macro to it. You could do mke2fs, dash T for the file system you want. We want ext3, um, and then pass it to the options as well. Can also be used instead of mkfs.ext3. So I think in this case you still would have to pass it all these parameters, but this is actually, I find, pretty usable. So just probably go with that. All right, so the next one is using parted. What is the command to create a 300 megabyte ext4 partition starting at 500 megabyte on the disk? Okay, so using parted, what is the name to create a 300 megabyte ext partition? Oh, what is the command to create that? Starting at 500 megabytes on the disk. So let's see if I can piece it together again. It's kind of cheating. I wish I could just yeah, I wish I could come up with this on my own here. So it should be pretty easy. Yeah, so we can do, so it would be so now this is for an empty disk. Let me get the yeah, so let me get the question here queued up in my find so I can find that easier. Then we'll go up here. Let's read the question more carefully. So what is the command to create the partition? So it's not an empty. So we already have the partition scheme as far as I know. And if we didn't, it would just be GPT. It's pretty much always going to be that in the modern world. So creating a partition. So we can assume this is done. So the command is mkpart. So we're going to do mkpart, and then we've got to feed it an option. So it should, yeah, it'll be mkpart primary ext4, and then 300 and then yeah, 500 300, I think. All right, so let's see what the answer is. All right, so the answer is use mkpart primary ex4 500. Oh, and okay, I got this wrong. 800, because 800 minus 500 is 300. So this is the end. Remember that you will have to create the file system using mkfs.ex4, as parted does not do this. So this is to create the partition, but you can't really do anything with the partition unless you have a file system, which you create using another command. You use the mkfs.ext4 command. All right, so now we're back to the last guided exercise. Imagine you have two partitions, one on /dev/sda1 and the other on /dev/sda2, both 20 gigabytes in size. How can you use them on a single BetterFS file system in such a way that the contents of one partition will be automatically mirrored on the other, like on a RAID 1 setup? And then how big will the file system be? So my answer to that, I think it'll be 40, right? Because it's just the two of them. Now, for some reason, I only have one match here. Let's try to get it so that I have two matches. Okay, there we go. So we're learning about BetterFS. So let's go back to BetterFS. And is this using parted? No. We'll go up to the BetterFS section. It was pretty much near the top. This was a really meaty section, so hopefully I remember this. All right, so here's BetterFS. So, yep. So it's the same thing. You do mkfs dot and then uh, the file system you want to use. We want to use the BetterFS file system, and then if we want to do it across disks, um, we can just give it two, um, yeah, into one big partition. So that's my answer. It's going to be mkfs.betterfs space, and then you feed it two disks that you want, and then it's going to be 40. So let's see what the actual answer is. So the actual answer is use mkfs.btrfs. Good. Then feed it the first partition. Good. Feed it the second partition. All right. And then I got the last part wrong. The last part is -m RAID. The resulting file system will be 20 in size. I got that wrong as well. As one partition simply acts as a mirror of the other. So should have known that. Let's go back and look at the writing and see if we can find that -m option. All right, so here we go. Here's that -m option. So hopefully we can read all about it. All right, so I don't really see anything about the -m option. I just see it used in an example. Oh, here we go. So to specify how metadata will be distributed in the disk array, use the -m parameter. Valid parameters are RAID 0, RAID 1, RAID 5, RAID 6, RAID 10, single, and dupe. So it kind of puts another variable at play here. So imagine you have two partitions. So let's imagine that we've got one SDA1 and the other on SDA2. Both are 20 in size. Now here's the key. How can you use them on a single BTRFS position in such a way that the contents of one partition will automatically be mirrored on the other? Oh, okay. You know what? Like on a RAID 1 setup. Okay, I thought it was going to be kind of like a Cisco question where like they'd leave this part up and you just need to know that it was RAID 1 based on like that was part of what they were testing on you on, is like if you knew that meant it was a RAID 1 or not, and they were testing you on like what you would feed it after the -m, and then you put in RAID 1 because you knew that RAID 1 was such a way that the contents of one partition will be automatically mirrored on the other. But it looks like hopefully the test won't be like that because the training materials that go along with it are not. But you never know. Maybe it will be that way. So how big will the file system be? Well, it says it right here in the question. It's going to be mirrored. So it's going to be 20. All right, so moving on to the explorational exercises. Let's see what we got on the clock. 13 minutes, looking good. So explorational exercises. Number 1, continue a 2 gigabyte disk with an MBR partition table and the following layout. All right, so here's the following layout. We're missing partition 2. Can you create a 600 megabyte partition on it? Why? So my answer is yes. Because you could, well, actually, let's see how big the disk is. So the disk is 1.9 gigabytes. So the final, so the end of it is you can create a 600 megabyte partition because you can add partition number 4. And the size of the disk is large enough to have 600 bytes after this. So So that's my answer. It looks like you also might have the size. Now, this is 600 megabytes. I'm not sure what's going on here. But let's go with my original answer and see if I'm right or wrong. All right, so the answer is no, you cannot. I was completely wrong. Because there is not enough contiguous space. The first clue that something is off is the list of devices. You can have /dev/sb1 and /dev/sb2, but or you have that's what's shown there, and I noticed that. I called that out, but no /dev/sdb2. So something is missing. Then you need to look at where a partition ends and the other one begins. Partition 1 ends at this sector, and partition 2 starts at this sector. So I did notice that as well. So that's a gap of over 1 million sectors. So at 512 bytes per sector, so we can see that the bytes per sector are right here, the sector size. That's like 536 million bytes. So if you divide it by 1024, hopefully you get a calculator on the exam if you get these kinds of questions. You get 524,000 kilobytes. Divide it by 1024 again, and you get 512, and you need 600. So this is the size of the gap. But why can't you just put it at the end? Anyway, if the disk instead of is, it says it. If the disk it 2 gigabytes, then we wave at most. I think this meant to say have. At most another 512 megabytes after partition 3. Okay, so I just did my math wrong. I kind of eyeballed it. I didn't pull out the calculator, and it seemed like it was big enough, but it was not. And so even if you have a total of around 1 gigabyte allocated, the biggest contiguous block is 512 megabytes. So there is no space for a 600 megabyte partition. So you really got to understand what they mean here when they say start and they mean end. What they mean is these are the sectors that you start and end at, and each sector is 512 bytes. So to get the total size of it, I mean the total size of it is listed here for each of these. So already we know we're taking up quite a bit of this disk. But the thing is, since this is a DOS partition, it has to be contiguous. So we can only slot it in between the contiguous space between B1 and B3. Or after B3. So we have to be able to do those calculations to know what is the size of a hypothetical B2 that we could fit in here, and is that size greater than or smaller than the size of the real partition that we want to create, which is 600. And we have to be able to do that for this missing block here and for the space after B12. I tried doing that. I knew I had to do that, but I didn't really put a lot of effort into a pull of the calculator, and my intuition about how big that size was wrong, because I didn't have as good of an understanding of what these numbers mean here as I do now. These are the sectors, and each sector is 512 bytes. So what you need to do is take the start sector, you need to minus it by the end sector, and then you get the total number of sectors that constitutes the space you have from here to here. And then you need to multiply that total number of sectors by 512 bytes. Then you can divide it by 1024 to get kilobytes, divide it again to get megabytes, and if you so wish, divide it again to get gigabytes, but where we're asking for megabytes here, for 600 megabytes. So just divide by 1024 two times, and if that number you get is over 600, the answer is yes, you can create it. If not, then the answer is no. Um, but honestly, I think it's because it's in yeah. So that's my answer, and I'm sticking to it. Let me read the answer one more time because there was one at the end. So it said, if you divide it by, so you get the bytes, and you get, so this is the size of the gap. If the disk 2 gig, then we wave at, let me fix this. So if the disk is 2 gigabytes, and we have at most another 512 gigabytes after partition 3, even if we have in total around 1 gigabyte unallocated, the biggest contiguous block, yeah, so this is just reinforcing the idea of something that's contiguous. So we start here, we have this gap here, so even though we have enough space on the disk to accommodate the 600 meg partition, if we put it after SB3, this space that is empty prior to SB3 does not count because it is not contiguous. Alright, so the next one is on a disk at /dev/SDC. We have a first partition of 1 gigabyte containing about 256 megabyte of files. Using parted, how can you shrink it so that it has just enough space for the files? So if I remember, there's a like a hotkey. I forget what the hotkey was, but we definitely need to go to the resizing section. And we need to read the question pretty carefully here. So, and I want to get it to match on the answer as well. So I'll delete everything until that happens. Okay, there we go. So, okay, so there we go. How can we, so now we're not talking about the file systems here, we're just talking about the partitions. We don't have to talk about the file systems at all. So let's go to the section on parted, and then the section on resizing partitions. So here we go. Now there are different kinds of partitions. Oh, you know what? So we've actually got another typo here. Yeah, this, unfortunately, I've got a lot of a lot to say about this lesson. It's really not been very good in my opinion. We've got all kinds of typos that conflate file systems with partitions. So an EX234 is not a partition; it's a file system. So this is wrong, and it's yeah, this is wrong. It should say resizing EX234 file systems, and then before that, we're going to have instructions for how to resize partitions. Okay, but anyway, the answer is resize part, and then let's see the question again. Yeah, so we're gonna have resize part, and then to shrink it. Um, so we can just do resize part. Oh, these are for file systems though. I'm so confused. I think it actually might be conflating it again. Because it's saying, like, how can you shrink it? Like, yeah, it's I think it's conflating partitions with file systems again. Let's see what the actual answer is. And we can see, it doesn't match with the original question. So like, see how it says on a disk at /dev/SDC, we have a first partition of 1 GB containing about 256 megabytes of files. So now down here it says containing an ex4 file system. Up here it doesn't say anything about a file system at all. So we've got two different questions here in the questions and answer. And the second question is better because this word here, using parted, how can you shrink it? So now, yes, it is an ex4 file system. That was an absolutely critical component of the question that was just completely left out here. So how can you shrink it? Up here, how can you shrink the first partition of 1 gigabit on the disk SDC? So SDC1, how can you shrink SDC1? Well, you would shrink it the way you would shrink partition. But the real question being asked is, how can you shrink the file system on SDC1, which is totally different. So my answer is that -M, because now I know that it's actually asking about resizing a file system and not a partition. So this is a multi-part operation. First, you have to shrink the file system using resize to FS. Instead of specifying the new size directly, you can use the -M parameter so that it is just big enough. So resize to FS -M /dev/SDC1. Then you resize the partition itself with parted using resize part. Since it is the first partition, we can assume that it starts at 0 and ends at 241 because that's the size of our file system. So the command is resize part 241M. So that's interesting because you got to know that you do the file system first, because otherwise if you did the partition first, it would be the file system would be too big for it. So this is the kind of thing where, like, if you do this every day as part of work, but you don't know what you're actually doing when you try to do it in some other context, you could get this wrong. You could try shrinking the partition before you shrink the file system and just totally realize you've been doing this for 20 years and you had no idea what you were doing the whole time. So it's important to understand that the file system and the partition are two different things, which is hard to learn from this because it often conflates the two, and we can see it's doing that here. It's asking how we can shrink it, meaning the first partition on SDC1, so that it has just enough space for the files, and then it doesn't say anything about the file system, which is important. So the real question is down here, where how can you shrink it means how do you shrink the ext4 file system? And the answer is you use resize to FS with a capital M to make it the same size as the underlying partition. And then you resize the partition with resize part. It's the first partition, and then you make it the size that you wanted the file system, 241 megabytes. So yeah, unfortunately we got poor marks for this learning materials. Not every learning materials can be high quality. So this is the power of using the AI, using other resources. So let's continue. I might need to take a break. There's only 3 more questions to go. So, you know what? I'm going to take a break because then we can really close this out. So I'll be right back. All right, I'm back. Mic check. Let's do a static check. All right, looks good to me. So, yeah, I'm just so close. It'd be a crime if I didn't just close this out. So we're on number 3. Imagine you have a desk at /dev/SDB, and you want a desk. Imagine you had a disk there. That might be kind of difficult to imagine. I'm still imagining a desk. And you want to create a 1 gigabyte swap partition at the start of it. So using parted, you create a partition with make part primary Linux swap 0 1024 megabytes. Then you enable swap on this partition with swap on /dev/sdb1. But get the following error information. Swap on /dev/sdb1 read swap header failed. What went wrong? Oh, this is interesting. Okay. So I'm guessing you don't have a file system. Let's see what we get for in the writing. Yeah, so the partition has to be of a specific type, set up with a proper utility. So I'm thinking there's something wrong with that. So you know what? I think that's going to be my answer. The partition was not set up with the proper type using the proper utility. Okay. All right, so that's my answer. Sticking to it. Let's see what the real answer is. All right, so the real answer is you created a partition of the correct type Linux swap, but remember that make part does not create a file system. You forgot to set up the partition as a swap space first using make swap before using it. So you have to create a swap space file system. So what we did is we did the make part, but we need to do make to fs as well. So we can see here make part or not make to fs, make swap. That's for the swap file system. Okay, so there we go. Made our swap file system, and everything's good to go. So the problem was we created our swap partition. We did that here, but we didn't create our swap file system. All right, so the next one, during the course of this lesson, you were trying out some commands in parted, but by mistake deleted the third partition on your hard disk. You know it came after a 250 megabyte UEFI partition and a 4 gigabyte swap partition and was 10 gigabyte in size. Which command can you use to recover it? So I remember this, but I don't remember it super clearly. I do remember where I read it, and it looks like this is one that doesn't really overlap that much with the answer either. So let's go and read the question given in the answer, but let's try not to read the answer because we saw just how much it was different. It was really impossible to get one of the earlier questions correct the way it was written, because it was written with a number of errors that were not included in the question that was tied to the answer. So let's read the question without reading the answer, because the question is very different. So here's the real question. So during the course of this lesson, you were trying out some commands in parted, but by mistake deleted the third partition on your hard disk. You know it came after a 250 megabyte EFI partition and a 4. See, I think it was missing this whole second part here, and a 4 gigabyte swap partition, and was 10 gigabytes in size. So yeah, it's completely different. So what part of command can you use? Let's find out. So you can use you can use the rescue command, and then you plug in the size. The start is so remember from the question it was, so it's like 2, so like 4. You can start from 4. It doesn't have to be there, and then to the end of the disk. So don't panic. You have all the information you need to cover the partition. Just use rescue and do the math. You had a 250 megabyte plus 496 megabytes, so 4 times 1024, so converting the gigabyte to megabyte before it. So the start point should be around 4,346 megabyte plus 10.240 megabyte, 10 times 1024 in size. It should end at 14.586 megabyte. So rescue 4346 M and 14586 M should to the trick instead of do the trick. It should to the trick. I'm not sure what that means. You might need to give some slack to rescue, starting a little early and ending a little late. A little late, yeah. Depending on the geometry of your disk. Lots of errors in this one. Kind of too much content packed into one lesson. They should have done this in 2 lessons. So not really that happy with this. And there's a lot of content, but what can I do? It's kind of beyond my control. There's not even like a feedback button or anything like that. All right, so one final question. Imagine you have a 4 gigabyte unused partition on /dev/SDA3 using fdisk. What would be the sequence of operations to turn it into an active swap partition? Okay, so it's 4. Okay, so the first thing you need to do is okay, so I know this one actually. So what you would need to do is, we already have the partition there, so you would need to modify the partition to make it a swap partition. So I'm not sure if you could modify it. So you already have the partition there, so I think you might actually need to delete the partition because it's not created as a swap partition. So you either need to delete it or you need to like recreate it. But I guess let's just say first you need to delete the partition, then you need to recreate it as a swap partition, then you need to create the swap file system. So first, change the partition type. Okay, so you don't have to delete it. You can change the partition type to Linux swap 82. Write your changes to disk and quit. Then use make swap to set up the partition as a swap area. Then use swap on to enable it. So for the most part, I got it right. I didn't know whether or not you could change it after it's already been created, or if you had to delete it first. The answer is you can change it. I got this part right. You have to set up a partition file system. And this part I got completely wrong. You do need to turn it on. All right, so that's it for this lesson, except for the summary. In this lesson, you learned how to create an MBR partition table on a disk with fdisk, and how to use it to create and delete partitions. How to create an MBR partition table on a disk with gdisk, and how to use it to create and delete partitions. How to create X2, X3, X4, XFS, VFAT, and XFAT partitions. how to use parted to create, delete, and recover partitions on both MBR and GPT disks, how to use resize EX2, EX3, EX4, and better FS, missing an F here, partitions, how to create, set up, and activate swap partitions and swap files. The following commands were discussed in this lesson: fdisk, gdisk, and then every variation of makefs, which just calls it's just a macro for another tool. So, and then we have one for each type of file system that is commonly found. So ex2, ex3, ex4, xfs, vfat, xvat. They even have it for betterfs. It's not listed on here. Then parted, we learned about betterfs. We learned about make swap, and then swap on and swap off to turn on or off your swap file systems after you have created them within a swap partition. All right, so that's it for this lesson. Stay tuned for the next lesson.